Let's motivate a powerful method of Lagrange multipliers to deal with a system first subject to a single holonomic constraint f as a function of coordinates and time equals to 0. The constraint is holonomic because it doesn't depend on velocities. Note that the constraint itself cannot change the form of the Lagrangian for the correct solutions of q as a function of time, all of them. Remember that in my notation, a set q means generalized coordinate sub 1 all the way to generalized coordinate sub n. So in other words, the Lagrangian form should still be just kinetic energy minus potential energy. On the other hand, this holonomic constraint must change the generalized coordinates themselves so that they obey this constraint. A way to proceed is to write a modified Lagrangian, we'll call it L star, which would consist of the unconstrained Lagrangian plus another part, which will disappear when the constraint is met. In the most general way, we can write this additional part as some function of time, lambda, times the constraint. Note that this part here is 0 for solution q of t, for the true solution that we are trying to find. The unknown coefficient, lambda, is called the Lagrange multiplier. Even though this extra term vanishes when the constraint is met, it doesn't vanish for variations around the true solution q of t. Thus, we expect to get from this modified Lagrangian new equations of motion that should now incorporate the constraints. Let's proceed with the usual Euler-Lagrange formalism. We write the new equations of motion for each component q sub I as partial derivative of modified Lagrangian with respect to generalized coordinate q sub I equal to full derivative of time of partial derivative of modified Lagrangian with respect to velocity q sub I dot. And then we obtain the following equation of motion. On the left hand side we have partial derivative of unmodified Lagrangian. So this Lagrangian is unconstrained Lagrangian plus a term that comes from the Lagrangian multiplier and partial derivative of f with respect to coordinate q sub I equal to full derivative of time with respect to partial derivative of unconstrained Lagrangian with respect to velocity q sub I dot. These n equations plus the constraint itself now form the equation of motion for the system subject to this holonomic constraint. Note that on the left hand side we have the generalized force, and this term here in fact is the force due to constraint. Generalized force due to constraint. What if we have more than one holonomic constraint. If many constraints f sub j, same holonomic, only functions of positions and time, where j is from 1 to number m, then we write a modified Lagrangian as unconstrained Lagrangian plus the sum of j from 1 to m of different Lagrange multipliers lambda sub j as a function of time times f sub j. The resultant equations of motions will look as following. We'll have unmodified Lagrangian derivative with respect to q sub I plus a sum of j from 1 to m of lambda sub j times partial derivative of f sub j with respect to q sub I equal to the right hand side full time derivative of unconstrained Lagrangian with respect to velocity q sub I dot. Note the j here and the I subscript everywhere else, plus all of the constraints listed here. So f sub j equals 0. So we will have n differential equations since I goes from 1 to n, and m constraints since j goes from 1 to m. Solving this now gives us the equation of motion of a system subject to m holonomic constraints.